Happy Monday, part 2. Any questions about things? Or comments? Questions about Brexit? Okay, I just handed out the attendance register. Everybody could sign that. If there are any questions or comments, please let me know. I think today will be probably the last normal lecture. I think we'll have a revision lecture next week. So if you have questions about the tests, you can bring them to that lecture. And there is a week of lectures when we get back from Easter, but the Monday is a holiday that week. So I don't have scheduled lectures on the Monday. So if you start to cry and you need tissues, let me know. I have tissues in my backpack. So here is a little preview of today's focus topic discussion. It's called texture-based flow visualization. We've been talking a lot about FlowViz, and we were talking about direct flow visualization. Then we talked about geometric flow visualization. So direct was like glyphs and color mapping. Geometric was with streamlines and path lines, timelines, streak lines, stream surfaces, path surfaces, and streak surfaces. This is another category of flow visualization techniques called texture-based FlowViz. And these look much different, as you can see, than the other ones. We're using textures. We put the textures on the flow, and then we distort them or smear them to reflect the flow properties. And that's what that looks like. So with all of the geometric FlowViz techniques, we had these challenges. One was where to put them, position them, like streamline seeding, for example. We never talked about stream surface seeding. It does exist. We don't really have time to cover it in this lecture. And how to construct those objects. Here, the challenge is actually different. It's more like the textures generally cover the FlowViz domain. They usually just cover the whole thing, like this covers the whole 2D domain, for example. So there's not necessarily a seeding challenge, but the challenge is more like computation. Like, how do you get this kind of algorithm to work quickly? The first versions of the algorithms were very slow, just like a lot of the first versions of many of the algorithms out there that are introduced. And then the question is, how do we make them fast? And so this is an example of what texture-based flow visualization algorithm can look like. This is one of the first ones for unsteady flow or time-dependent flow. The first ones were for steady-state flow. Now we're looking at time-dependent flow, 2D time-dependent flow. Does it look interesting? I think it looks very interesting. I love watching the texture-based flow visualizations because of their sort of very lively, organic nature. It makes the study of fluid flow very, very interesting, actually, these kinds of visualizations. I find them absolutely fascinating to watch, actually. And it's one of my favorite topics in the domain of visualization, generally speaking. And so that's what we're going to be talking about, something like this. This is, remember when we were talking earlier today about dye and streak lines being analogous to the advection of dye. This is a kind of another version of that same concept, but it's more realistic in some ways. That is actually a wind pattern over Europe, but we didn't see the European map in that example. I do have one with a European map, I believe. So that one is with a map. So this is what the weather pattern looks like just before Brexit. You'll notice a vortex swirling over London, a low pressure region just over London, about to suck everything in before it collapses. But that is texture-based flow viz. And the transparency of the texture is changing. So it's more transparent in low velocity areas and more opaque in high velocity areas, regions of high velocity. And we'll show, just for fun, because we like to have fun, show another texture-based flow viz example. Nothing to do with the weather, but more about our favorite engine some of our favorite engine simulation data. And this is the same idea, but extending the algorithm to surfaces. So can we do something about surfaces rather than, for example, just 2D planar flow? Anybody recognize that data set? We've seen that before in other lectures. That's from an engine simulation. And it's actually a combustion chamber as part of your engine and 2 intake ports. The intake ports are responsible for injecting fuel into the combustion chamber and also releasing the exhaust, so to speak, or the burnt after the burn cycle. And when you extend this kind of thing to surfaces, there are some extra complexities that are involved, like edge detection, for example. We're not actually going to talk about this particular algorithm today, but a predecessor, one of the earlier versions, called Line Integral Convolution, which is one of the first texture-based flow visualization methods to be introduced. This is the cooling jacket. So that flow is mapped to speed as well. There's a color map that indicates the speed. So the different speeds are reflected by the color. This is to show that the method supports interactive zooming, so you can zoom in on anything and get more detail. That's one of the nice properties of the texture-based flow-viz methods. This is not engine simulation, but the simulation of blood flow, and that thing is an aneurysm. So that's an area of blood flow that is no longer circulating as efficiently as it used to, and the blood's getting trapped into this kind of pocket. And the algorithm, this is a demo of an algorithm being applied to an unsteady mesh, so a mesh that is actually changing over time. The bottom of that mesh is a piston head. You don't actually see the piston head. You only see the combustion chamber part. And that's what the fluid looks like as it at the surface of the combustion chamber as it's being injected into the combustion chamber. And that is 1/2 of a valve cycle. So some of you that study cars know that when you drive a car around, it's hundreds of valve cycles every minute. So typically like 1,000 valve cycles or thousands of valve cycles every minute. So it's very much slowed down, slow motion version. Look interesting? That would be a fun assignment 3, wouldn't it, to implement such an algorithm. Assignment 3. So let's look at this texture-based flow visualization in some more detail. So here is an introduction to one of the first texture-based flow visualization techniques, Line Integral Convolution it's called. So this texture-based flow visualization method provides a very nice overview of the flow. That's one of its nice properties. And instead of trying to compute, for example, polygons like triangles or quadrilaterals or something like that, or edges, it's all about textures. And textures are composed of, anybody remember what textures are composed of? I guess everybody's feeling very excited today. How about Sam Roberts? Sam? Do you remember what textures are composed of? Can anybody help out, Sam? Texels. Did we never mention that in this class? Maybe I didn't mention that yet. Texels, texture elements. Maybe I got it confused. Oh, I think I got confused because I remember we talked about pixels and voxels. We didn't talk about texels yet, did we? Okay. So texels, texture elements. And so it's all about operations on texels, or texture elements, which are just like pixels, but they're part of a texture. And this is an example of a texture-based flow visualization, right, on the surface of an object. And you can see it covers the whole object, so seeding is not necessarily a problem. The seeding is transformed into a texture mapping operation. And then the question is, how do you compute these lines, these kind of curvature, this curvature in the texture? That's really what it comes down to, the focus of these algorithms. How do you compute those curves? And by the way, those curves are similar to streamlines. So they're curves that are tangent to the flow. They follow the direction of the flow. So they're tangent and they reflect the orientation of the flow. In this particular example, you know that the flow moves this way just by looking at the object, but in general, you cannot tell which way is downstream and which way is upstream in this, like a static image like this. So here's an overview of the idea. For each texel, that's a texture element, let the texture value correlate with neighboring texture values along the flow or in the flow direction. There's a fancy term for that. It's called convolution. So sometimes we mention this word convolution, which is basically a weighted average, basically. Correlate for each texel, correlate the neighboring texture values along the flow in the flow direction, and do not correlate the texel values with neighboring texture values orthogonal to the flow. In other words, make sure they're not correlated orthogonal to the flow, only in the tangent direction, like along the flow, not like across the flow, let's say. And when we do this, the texture elements, if they're correlated in the direction of the flow, it gives us the illusion, kind of an illusion, but it creates a streamline-like pattern, a very dense streamline-like pattern, because texels are dense. You know, they're small. Pixels are dense, right? So texels can be very dense. And so the idea is you start with a texture that's essentially white noise. There's no correlation between any of the texels. It's just white or pink noise, another one. And then you start your computations that says, okay, let's introduce correlations between those texels that are following along the same flow path. That's the idea. And here it says smudge white noise. That means start to create that correlation. In other words, push those gray values in the direction of the flow. Push them there. Here is kind of a schematic of the idea. So there's this is what the flow data looks like in 2D. It's vector samples, and each vector sample is stored on a 2D Cartesian grid style. We've seen that before. We're very familiar with that. And in here, we're showing one texel or one vector value. And this is showing the same thing, but now there's an integration. There's a forward integration and a backward integration. Remember, we computed streamlines using numerical integration. Was that 1 week ago or 2 weeks? It's two weeks ago, I think. Yeah, 2 weeks ago. We computed streamlines using forward integration and backward integration. It's the same thing this time, but now when we compute the position of a streamline point, we're also moving this texel value along with us. So we're bringing a texel value along with us. That's what this represents. So forward integration, backward integration, and then correlate the texel values. Now here is the next element. This is the white noise input. So there's a white noise texture that's just mapped to the whole domain. And so it's hard to see, but actually this streamline has been projected down onto the white noise. And these texels, which have no correlation at all with one another to begin with, are then correlated with this operation, a convolution operation, which just means a weighted average along the streamline. And the output is the value of a texel, a grayscale value. There's a texel there, it's hard to see, but it's a texel and it has a grayscale value. And that grayscale value corresponds to all, it's like a weighted average of all the texels along that streamline, the streamline that passes through that texel. That's the idea. So we input the flow data. That's obviously, we need a vector field. And we input a white noise texture map, and we map the whole thing onto the flow. And then, that's usually pre-computed, by the way. Then we compute a streamline through that each point, forward and backward. And along the streamline, we sample the texel values of our neighbors, and we compute a weighted average of those values, and we store them at the point. So it's a big for loop that computes texel values one by one, and they're the weighted average of our neighbors along a streamline. Now, when we say weighted average, it just means that the closer the neighbor is to us, the more important their texel value is and the more weight it gets. So if we're looking at a neighbor right next to us, their white noise texel value is very important. It gets a very high weight. And that's what this Gaussian filter is referring to. And the result is called an LIC texture, or a line integral convolution texture. I think it's the name is very confusing, LIC, line integral convolution. It might be more intuitive if it's, instead of line, it was streamline integral convolution. But another simplification could be like streamline weighted average kind of thing. Weighted average streamlines in some ways. So the terminology is confusing. So it starts with the white noise texture, and then we can also call it a smoothing filter. So the white noise is smoothed along the directions of the streamlines in both the forward and the backward directions, or the upstream and the downstream directions of the flow for each texel. So this is an example. And that these texels have been computed one by one, right? Starting with the top left, forward and backward integration, and then the next texel, forward and backward integration, a weighted average of all the texels, and so on. So you can imagine that for every texel, computing a streamline for every texel is an expensive operation, like computationally expensive. And so the initial efforts on this algorithm were really centered around speed, how to make it faster. And you can see some of the nice properties. Some of the nice properties are the entire vector field is covered. There are no holes. It's a dense representation of the flow. But you can't see downstream and upstream, the upstream, downstream, and upstream direction in this static image. You can see some aliasing artifacts if you look very, very closely. But it's clear you can also see the properties of the flow, like turbulent flow, for example, with lots of vortices. Laminar flow refers to flow that is moving in a more or less straight line, not too Another property you can notice is you cannot exactly follow a streamline, for example, here. Like you cannot really, you can't be too sure about like here's a streamline and here's where it starts and here's where it ends, for example. So there is some visual correlation, but the visual coherency is not as, let's say, distant as with the discrete geometric object. And that's, arguably that's a good thing. So in this example, there's a white noise texture. However, the opacity is also changing there. So you can see through the texture. If there's a map underneath, it's good if you can see the underlying map. And the only way to do that is to vary the transparency. And the idea here is you can make the texture varying levels of opacity. You can assign an opacity to every pixel, or every texel rather. And in this example, the texels are fully transparent when the velocity magnitude is low. That's usually the way it works in these examples. The lower the velocity magnitude is, the more clear or the more transparent the texels are. So you end up seeing like the Great Lakes, for example. I'm sure you all recognize the Great Lakes. Anybody here ever seen a Great Lake before? You've heard of them though, hopefully. The Great Lakes, has anybody even heard of the Great Lakes? Like, heard of them, yeah? They do have a funny property. Do you guys know what the funny property is of the Great Lakes? Have you heard people talk about them? No funny properties?
Wasn't it something like, I'm down by the way, wasn't it something like the water's meant to flow between them or something?
Say it again?
I thought like they said something about the water's like meant to sort of go between them or something.
Yeah, they're connected. But one of the kind of unusual properties is you look at them and it looks like you're looking at an ocean, but it's fresh water. That's just, it's such a big thing. It's kind of weird to look at something that looks like the ocean, but then have it be fresh water. But anyways, this is an example of adding this. It's also called a velocity mask. It means like changing the texel opacity based on the velocity magnitude. That's also called a velocity mask. And we saw that term velocity mask in one of the videos, the demo videos. Here's the idea applied to surfaces, right? You can texture map surfaces. Sometimes that's easy, sometimes that's very difficult. And then apply the same thing. It does get more complicated when you apply the same idea to surfaces. And here the velocity is colored. I'm sorry, the texels are color mapped. So blue is slow velocity in this case, and red is high velocity magnitude. So we can see, we can add the orientation and the magnitude in the same image. But again, we don't actually see the downstream direction. We know the downstream direction because we can imagine that thing flying, but literally we cannot actually see the downstream direction if we're just looking at the texture. And that's just an image that kind of compares three of the classes of techniques, right? The glyphs, the kind of short streamlines are also called streamlets, and texture-based flow visualization. It's just kind of nice to see them this 3 side by side on the same data set in order of popularity, really, because the arrows are the most popular, followed by the streamlines. You don't see texture-based flow visualization that much as the other 2 classes of techniques, because the implementation is a little bit more difficult than the other techniques. It is possible to apply the same concept to 3 dimensions, but it gets more difficult to perceive the direction of the flow because you have overlapping flow in the depth direction, so to speak. So yes, it does work on this nice academic example, but you can see already that there's more of a uniformity with respect to color. The whites are not as white and the darks are not as dark when you start to try to apply it. Like this almost looks like uniform color. You know, it's starting to look more uniform. And the same is true here. But the person that made this image very, very carefully selected the region. It's a very careful region selection. It's not the entire volume, right, to get that nice 3D line integral convolution. But because there's grayscale texels here, and then there are more grayscale texels behind it, it starts to lose some of the contrast, the grayscale color contrast. So it's a challenging. It's not considered a solved problem with the application of 3D or 4D flow. There are solutions that exist, but it's not generally considered like completely solved in 3 and 4D flow. So those are the papers that talk a little bit about the algorithms in more detail. But now if you look at those papers, you'll be able to understand them much more easily now than if you didn't have this lecture. That's one of the basic, very first texture-based flow visualization algorithms, the line integral convolution algorithm. And since that time, there have been many variants and other developments. This one's called oriented line integral convolution, so we can see the downstream direction in this example. But you notice adding the downstream direction, something has been taken away in this example. And that is suddenly there's space between the texels, so it's kind of like a sparse version of texture-based flow visualization. You can tell it's moving in that direction, but there's some of the coverage has been taken away. And then what we saw in the video is texture advection, and that is when the texels are pushed in the direction of the flow, or the texel values. Right? If we look up the word advection in the American Heritage Dictionary, the term means the transfer of a property of the atmosphere, such as heat, cold, or humidity, by the horizontal movement of an air mass. Today's temperatures were higher due to the advection of warm air into the region. Another term is the rate of change of an atmospheric property caused by the horizontal movement of air or the horizontal movement of water as in an ocean current. But in this case, it's the horizontal movement of texels, so texture advection, as opposed to the more general case of advection. And so that's an acceleration of the original line integral convolution algorithm, so that we can look at unsteady flow. And we can look at that again. So now if we look at those examples again, you'll have a better idea. Let me just see this one. We didn't look at this one, I don't think. Let's look at this one. So this is extending, essentially extending. Oh, okay, is that the same one? It is the same one. So that's extending the original line integral convolution algorithm to unsteady flow to make it fast. Right? And that's what the sample white noise, that's the input white noise that we mentioned on one of the slides, what we just saw. So that's just taking the white noise and rotating it. Now this is taking that same thing but adding the convolution part, which is the smearing of the texels, the white noise texels, along the flow in the direction of the flow. You might recognize that flow because we talked about that in one of the lectures on numerical integration 2 weeks ago, the circular flow. And you can mimic dye advection, so it's just changing the color of the input texture, adding colors. Instead of making it white noise, it's now using colors, and then it looks like dye. And that's just a kind of synthetic unsteady flow in this example. You can see aliasing artifacts in this video if you look carefully. I don't know if you guys can see the aliasing artifacts, but on my screen it's pretty apparent. Yeah, you can see some aliasing artifacts here. That's kind of like a zooming in and out, even though it's not as applicable in 2D, zooming in and out, but that's kind of like a zooming in and out on a 2D unsteady flow. And that's the idea of actually applying it to. Now this is the winds over Europe example, but there's no map. So that's what the raw wind data looks like without integrating any map. And so it's hard to tell exactly where the things are located. But you can see that there's a strong air current from the north in a lot of the time steps, which means a cold weather front if it's coming in from the north. You can also notice, if you look carefully, a kind of pulsating effect, like something is coming and leaving, coming and leaving. It's like a low velocity pulsating effect if you look carefully. I don't know if that's really part of the data or not, or if it's a bug, but as it stands, it's fluctuating between low velocity and high velocity. I don't know if everybody can see that, but there's a global pattern, a global fluctuation pattern, like where the screen gets very dark and then light, dark, light. You know. But if it gets dark, it just means that the wind is slowed down, basically. And that means nicer weather, generally. So we'll look at this example. This is an example applied to surfaces that we saw already a few minutes ago. So that's 200,000 polygons. That mesh is composed of 200,000 polygons, and each polygon has velocity values stored at the vertices. So the velocity values are stored at the vertices, and it's those velocity values that are used to push the white noise texture in the direction of the flow. And this is just an example that normalizes the flow, so to speak, and makes all the velocity vectors the same magnitude. That's what that is. It's not necessary, but it's just a possibility. And when you apply it to surfaces, you need to insert some edge detection, some sort of edge detection knowledge. So that's demonstrating the extra edge detection knowledge that's built into the algorithm to keep the texel values from just being pushed over edges. You don't want texel values to just be pushed over edges. You want them to stop and change their value, so to speak, because then it looks like the flow is moving directly over an edge, and that's not nice because it's not what the engineers. It's not a very good reflection of what's really happening. It's not happening. So this is highlighting areas of low velocity, by the way. It's unusual because usually the high velocity is the interesting regions, but that is highlighting areas of low velocity, which are very bad in a cooling jacket. That's what makes your car overheat. And there's the blood flow simulation. So this is, again, mixing the texture. It's also mixing a velocity mask in there, partially because we need to be able to see the underlying surface. If we can't see the underlying surface, then it's not very helpful. So there's a blending operation between the surface geometry and the LIC texture, or the white noise texture. And the texture is animated, as you noticed already, and each texel value is pushed in the direction of the flow. Right, this is the half of an engine cycle example. So the idea of applying this to half of an engine cycle, or the cylinder there. It's mostly proof of concept, just to demonstrate that it is possible to apply this to a mesh that is time dependent, or a mesh that's changing over time. And that's just basically saying this algorithm is now fast. It used to be slow, but now it's fast. Any questions about that texture-based flow-based question?
Yeah, you said it used to be slow and now it's fast.
That's right.
What sort of speed up are we talking there? How much of it has changed?
So the original LIC algorithm to compute an image like this would take a few minutes, or maybe a minute, or something like that.
Is that a single frame?
A single frame. So it really wasn't practical to apply it to unsteady flow in the beginning. Now, the video I just showed you, it's running at like 20 frames a second. So it's very fast. You can apply it to unsteady flow. But there's also quite a long time of period that passed in between. Right? So LIC was published in 1993. Whereas that one we just saw on the surfaces, that was published in 2003, so 10 years passed of further work.
How much of that is due to algorithm change compared to hardware?
That is more difficult to answer, actually. I would say that they were both very important steps. Like the hardware getting better was important, and the algorithm getting better. They were both very, very important. Otherwise, it wouldn't run at 20 frames a second. How, like, exactly what percentage you could attribute to hardware speed up and what percentage you could attribute to software speed up or algorithm speed up, I don't know the answer to that. The only way I could know that answer scientifically is if I were to get the hardware from 1993 and run the new algorithm on it. That's the only way. If I were to use my imagination, I would say I would guess something like, the original LIC algorithm may be taking a minute to produce an image. And if I were to run the modern one, maybe it would take like 1 or 2 seconds. So it wouldn't be 20 frames a second. It would be like a 1 frame a second or 2 frames, or 1 frame every 2 seconds or something like that, if I were to just guess. Yeah. Any other questions? Those videos are on the YouTube channel, by the way, and these are the papers that they're based on. Then the next part of the lecture, or the topics, are feature-based flow visualization. We're not going to get into the depth of the feature-based flow visualization, but it is a 4th component. I don't know if you guys can remember, we had a slide about the 4 different subfields of flow visualization. And this was one of the slides, like, what is flow visualization? Feature-based flow visualization is all about this aspect. What should be visualized if you have a 4D flow? What subset do we actually visualize? And so feature-based flow visualization is trying to make a decision about what subset of the flow should we visualize, because we usually cannot see the whole thing at the same time. And so we look for things called features. Those are difficult to define because they're based on the user. If you ask a user, what subset do you want to see? Every user will have a different answer. Like, I want to see this, or I want to see this. If we look it up in the dictionary, a feature is a prominent or distinctive aspect, quality, or characteristic. Any subset of the domain deemed interesting by an onlooker. That's my definition. That would be the definition that's most applicable and most useful for this context. So feature-based flow visualization is the focus on and resulting depiction of a subset of the flow domain. That's really what it is. And an example would be, show me all the vortices, or show me all the areas of circular flow. That would be an example. And guess what? There's a feature-based flow-based pipeline. I know you guys love pipelines. I love pipelines, and that's the feature-based flow-viz. But essentially, the essence, this is the last slide, by the way. The essence is you input a vector field into the algorithm, and before you do anything, you don't do any streamlined computation, you don't compute any advection or texels, like, you don't do any of those computations. You decide, you search for the regions that you find interesting. Like, where are the subsets of the flow that are interesting that we want to focus on? So there's a search process. And then after the search process, the rest of the pipeline is similar to the traditional flow-based pipeline. So that's the idea. That's what this selection means. The selection means search for the interesting areas. Once you found the interesting areas, cluster them together and form groups in the flow domain. And then there's the visualization mapping and so on. Okay, I think we're out of time basically. Any questions before we stop? I hope that, I know you're all worn out and stuff like that. And I hope that maybe you can, I don't know, well, if you want, you have the option of thinking of exam questions for next week, if you want to ask questions about the exam.
Well, I've got a bit of a question. Basically, what's the process about going through to get an extension on the coursework for medical licenses?
What's the process of getting an extension on the coursework for medical reasons?
Yeah.
The normal way we do that is you just show documentation. Like you have a doctor's note and say, I was ill before the deadline, and here's my doctor's notes, and then you get some extension. That's
Great.
the idea.
Great, lovely. And does that go to the office?
Say it again.
Do you put that into the office?
You can give it to the office if you want, the student secretary. That's a good choice. Yep. Yep. Any other questions? Okay. Happy Monday and happy April Fool's Day. Coursework 2 did not get canceled, by the way. It didn't get canceled.
Was that a rumor?
I just made a joke earlier today. I think you missed it.
Oh, we did, yeah.
I made a joke right at the beginning of class that assignment 2 is canceled as a cruel April Fool's joke. By the way, Luke, before you go,